In this video, we'll explore a powerful algorithm for uncovering hidden outliers in your data, the isolation forest. The isolation forest is an outlier detection algorithm based on the process of isolating data points. It builds multiple isolation trees and uses the number of splits required to isolate each observation as an anomaly score. Outliers tend to be isolated with fewer splits compared to normal data. For example, consider isolating the orange point in the figure below. In the left diagram, 5 splits are needed, whereas in the right diagram, only 3 splits are sufficient. This illustrates that normal data are difficult to isolate through partitioning, while outliers are relatively easier to isolate. For reference, while a conventional decision tree partitions data to predict a target value y, the isolation forest is an unsupervised algorithm and does not require y. Isolation forest works as follows. A subset of observations is randomly selected from the entire dataset, and binary partitioning is repeatedly applied to build a single isolation tree. For example, from a dataset of 1,000 points, 700 might be randomly selected to create one tree, and this process is repeated to build a total of 100 trees. Since each tree is based on a randomly selected subset, some data may overlap or be omitted across trees. For each isolation tree, the path length of each data point is calculated. Outliers are easier to isolate, requiring fewer splits, so longer path lengths indicate normal data, while shorter path lengths indicate outliers. The figure below visually illustrates the splitting process of the isolation forest. The red outlier can be isolated with just one binary split. In contrast, the blue points, representing normal data, are mixed with other points and require more splitting steps to become isolated. This difference, outliers needing fewer splits and normal points needing more, is the core principle behind the isolation forest. Let's take a closer look at the isolation forest using the given figure as an example. The path length refers to the number of splits from root node to terminal node, where observation X belongs. That is, the number of splits required to isolate X. In the figure, the yellow point on the plot is far away from the other green points. To isolate this point from the dataset, a first split is made based on X, 1 equals 10. This immediately separates the yellow point, so only one split is needed to isolate it. On the other hand, the brown point at coordinates 6, 7 is clustered close to the green points. Isolating this point requires 4 splits, more than the yellow point. This illustrates that the shorter the path length, the higher the likelihood that a data point is an outlier. In conclusion, since the yellow point is isolated with very few splits, the isolation forest identifies it as an outlier. The isolation forest consists of multiple isolation trees, and the structure or number of terminal nodes can vary between trees. Because of this, path lengths of observations cannot be directly compared, so they are normalized based on the size of each tree. The anomaly score is calculated using an exponential function of 2 as shown in this slide, where E of h of x is the average path length of observation x, n is the number of data points in the tree, and C of n is the expected path length required to isolate a single observation from n data points. Thus, the smaller E of h of x is closer to 0. The closer the anomaly scores to 1, indicating a higher likelihood of being an outlier. Conversely, the larger E of h of x is, the closer the anomaly score is to 0, indicating a higher likelihood of being normal. All right, next, let's talk about one of the methods used in AI to detect outliers, called the one-class support vector machine. Let's first take a look at support vector machine. SVM is a supervised learning model used to classify data from different classes based on a decision boundary. How this boundary looks depends on the dimensionality of the data. In 2D, it's a line, in 3D, it's a plane, and in 4D or higher, it's called a hyperplane. The data points that play a crucial role in SVM are called support vectors. They are the points closest to the decision boundary. The distance between the decision boundary and the support vectors is called the margin, and the main goal of SVM is to find the hyperplane that maximizes this margin. The one-class support vector machine, one-class SVM, is an unsupervised learning-based algorithm used to distinguish between normal and anomalous data, primarily using normal data only for training. This model works by first mapping the normal data into a high-dimensional feature space. It then learns a decision boundary that encloses the normal data. If the data doesn't have an explicit normal label, the algorithm typically proceeds by assuming the vast majority of the overall data is normal and training on that, considering a few points that fall outside the distribution as outliers. The decision boundary is positioned as far as possible from the origin. The region inside the boundary is defined as the normal data region, while the area outside the boundary, closer to the origin, is defined as the anomaly region. In this way, the one-class SVM operates by learning the distribution of the normal data and then classifying any data points that fall outside this boundary as anomalies. In one-class SVM, this parameter is defined as the distance from the origin to the decision boundary. This distance serves as the criterion for setting the boundary that encloses the normal data. The extent to which each data point has violated or strayed past this boundary is represented by the variable xi. This value evaluates whether the data point has exceeded the permissible limit outside the decision boundary. If a data point is located inside the boundary, it's considered normal data. Even if a data point is located outside the boundary, if its x value is small, it's judged to have only slightly crossed the boundary and may still be tolerated as normal data. Conversely, if x is large, the data point is considered to have strayed significantly past the boundary and is likely to be classified as an outlier. Based on these principles, the one-class SVM maximizes the distance from the origin to the boundary, while trying to include as much normal data as possible within the boundary. This process effectively learns the distribution of normal data and enables the detection of anomalies. In the diagram, the dashed line represents the hyperplane decision boundary, denoted by the function f of x. This function is defined by a specific equation as follows. The value of this part indicates which side of the decision boundary the data point x is located on and how far it is from the boundary. Therefore, f of x equals 0 represents the decision boundary itself. If f of x is greater than 0, the data point is located inside the boundary, meaning it is in the normal data region. If f of x is less than 0, the data point is located outside the boundary, meaning it is in the outlier region. Furthermore, when considering the allowable deviation at xi, a data point located slightly outside the boundary can still be regarded as normal if it falls within the allowed range. Specifically, if f of x is greater than minus xi, even though the data point is outside the boundary, it is considered to be within the allowable range and can still be classified as normal data. However, any data point that goes beyond this allowable range, that is, f of x less than minus xi, is classified as an outlier